Okay, what's up, everybody? Welcome back to another fun day of proof set theory and logic. In case you missed the discussion that began today's lecture, or preceded today's lecture, the syllabus, someone very, very nicely pointed out, lists the final as being on Wednesday when it's on Monday. This is in Campus Connection, so hopefully if you look there, you see it. I will send an announcement about this. I do have a final on Wednesday, but it's a different class. Yeah, my bad. I put it in the wrong one. So I will send an announcement about that, but hopefully this doesn't mess up anyone's schedule. After all, when they have you sign up for classes and they schedule finals, they do it so that they hopefully don't overlap. So I think it should be fine, but all the same, good to know. Okay, so if you guys recall, last time we were talking a little bit about denumerable sets. So we proved just at the end of last time, we proved that if A is a subset of the naturals, then A is countable. Recall really quickly what this means. We say a set, let's call it S, is 1. We're going to put a couple of different things here. So this was definition in your lecture notes, 7.12. It is denumerable if S is equinumerous with the naturals. 2, countable if S is finite or denumerable. And finally, if it is not countable, we'll call it uncountable. One of my favorite repeated silly themes in mathematics is when you have definitions that are obvious, right? When you're like reading a book and it's like, it's uncountable if it's not countable. We'll say that it's, un-x if it's not x, right? Very, very common theme, kind of a silly one. But all right, cool. So we showed this last time. Basically, the idea is that we're building up to seeing that uncountable sets actually exist. Yeah? So that's kind of the question. Do uncountable sets exist? How do we get them? That is, what earthly process results in a set so large that you can't even count it? It turns out that we'll get there. We'll have a nice, satisfying answer to this in some sense. But so far what we're exploring is basically, hey, can I somehow grab countable sets and put them together in some way to get an uncountable set? And so far the answer has been kind of resoundingly no. Basically, so like when we first started this out, we said, okay, can we take denumerable sets and maybe take the union of them and get a denumerable set, or get an uncountable set? The answer was no. If you take the union of denumerable sets, you get a denumerable set, and so on and so on. So actually, oh wait, no, I'm looking ahead. We have not proved that. We will get to that very momentarily here. But basically the idea is, hey, can I somehow put together some relatively large sets, the largest ones we've seen so far, denumerable sets? Can I put them together in some way to get an uncountable set? And maybe we would say something like along the lines, so for instance, what we proved last time, we said, okay, if you've got a subset of the naturals, then it's countable. And we know that if A is denumerable and B is equinumerous with A, then B is denumerable as well. And we started out with an example where we said, hey, what about the evens and the odds? right? We took the natural numbers and we said, what about the even naturals? The even naturals are also denumerable. And so you can look at it and say, hey, look, the odd numbers, those are also denumerable. We constructed examples and we said, put those two together and you get all the naturals. So it seems sort of like if you take two denumerable chunks of the naturals and put them together, well, it doesn't look like you can break this countability barrier. That is, you get back something countable. You get back the naturals itself. So maybe you would say, okay, maybe we just picked the wrong subsets. Maybe the evens and the odds are like too nice. Maybe I can pick a different subset. Unfortunately, this tells us that that won't really work, right? If we grab a subset of the naturals, it is countable. And so its complement, which is also a subset of the naturals, is also countable. And so you put them together and you get the naturals, and that's countable as well. Okay, so it's not the case that I can just take chunks of the naturals and somehow union them together and get something uncountable. So how on earth am I going to get there? Well, let's keep seeing how much further it goes. So here is a quick corollary. Corollary has one R. There we go. Corollary. A subset of a countable set is itself countable. That is, countability is something that is inherited from supersets. So if you have a set and you say, is it countable? Well, can you embed it in a countable set? If you can, it is. Okay, cool. So how do we get here? Well, if you look at it, it says a subset of a countable set is countable. We've proved that any subset of the naturals is countable. And we've shown that a denumerable set, well, let me specifically reference the result. We showed that if A is denumerable and B is equinumerous with A, then B is also denumerable. So if you take a denumerable set and it's equinumerous with some, so take a subset of a countable set. Either this set is finite, in which case it is certainly countable, or it is not finite. In that case, what? So a subset of a countable set, the countable set is either finite or denumerable, right? So if you take a subset, it will either be a finite set or it will be some other subset that is not finite. If it's some other subset that's not finite, then since the countable set is either denumerable or finite, it is either itself a finite set and it has no subsets that are anything other than finite, or it is itself denumerable. So it can be put in bijection with the naturals, since the naturals are equinumerous. So any subset of it can be put in bijection with some subset of the naturals. Hence, that subset is countable, right? See kind of like the chain of reasoning there, basically. Okay, so subsets of countable sets are also countable. That's kind of a nice little fact. Another corollary that comes out of this, exactly along the same line of reasoning, is that a set A is countable if and only if, let me see if I can get this on the same line. A weird less than or equal to the naturals. That is, it's countable if and only if it has some injection into the naturals. All right, this seems reasonable. Why? Well, certainly, if there's some injection to a subset of the naturals, then it is equinumerous with some subset of the naturals. Hence, it is equinumerous with a countable set and must therefore itself be countable, right? Or, on the other hand, if A is countable, then it is either finite, in which case it can be put in bijection with some subset of the naturals, hence there's an injection to that subset, right? or taking that injection and extending it to the whole thing, right? Taking the inclusion, that's an injection into the naturals. Or it's denumerable, in which case there's a bijection to the naturals, right? Hence an injection, since every bijection is also an injection. Does that make sense? Okay, cool. So if we're feeling good about this, then let's go on to yet another corollary. All right. Kind of a lot of corollaries in a row here. A set A is countable if either of the following is true. 1, there is an injection F from A to the naturals. 2, there is a surjection F from the naturals to A. Now, this first one, I think, is relatively straightforward. If there's an injection from A to the naturals, well, that's exactly what this weird less than or equal to sign means, right? Okay, cool. Now, if there's a surjection from the naturals to the set, what does that mean? What does that tell us?
Value in that set gets assigned to A.
Yeah, okay, so totally. This is exactly the right idea. So basically the gist of it is that if there's a surjection from the naturals to A, well, it might not be an injection, right? This might not be a bijection. That is, some things may get hit too many times, right? Okay, so take a subset of the naturals such that everything in that subset hits only one thing in A. Then you have an injection from the naturals, or a subset of the naturals, to A. That is, you have a bijection now between a subset of the naturals and A. Does that make sense? Here, this is the kind of idea. So if f of n is A, that is the image of the naturals is all of A, then for all A in big A, there exists some NA in N such that f of NA is equal to A. Pick one for each little a in big A. To form a subset S contained in N such that F restricted to S is a bijection. Then A is equinumerous with this subset, right? There's a bijection with it, yeah? But that subset is a subset of the naturals, so it's countable. Does this make some sense? That is, the only thing that can go wrong effectively with this surjection showing that the subset is countable is that it may not be an injection. Okay, so just restrict to a chunk of it where it is an injection. Yeah? The picture you want to kind of think of in your head here, if I want to jump to the next board, for statements like this, is something like this. So here, I'll draw like a kind of finite set looking case of it, since the finite set case really does model the whole thing. If I had like 1, 2, 3, and 4, and here I have a set with just like A, B, and C, well, maybe I have some sort of like a surjection like this. all I have to do now is pick a chunk of this set here such that nothing over here gets hit twice by things in that chunk. So 1 hits A, okay, we're good. 2 hits C, okay, we're good. 4 hits B, okay, we're good. We don't need 3. Yeah, we've hit everything on the right-hand side. So we can just essentially ignore that little piece right there. This is some proper subset right here. This is your subset S. And that does what you want. Yeah? That is, we've shown that this set here is equinumerous with some proper subset of the bigger set that you're surjecting onto the other one. And so, if we know something about the cardinality or, a property of subsets of the larger set, for instance, the first thing we wrote over there, a subset of the naturals is countable, then we know that this subset must also be countable since it's equinumerous with a countable set. Cool? Cool. Right on. Okay. So if we've got this kind of basic reasoning, this sort of nice little chains of equinumerosity, let's get to a more interesting theorem than all of these corollaries. How about this? The union of two denumerable sets is denumerable. Okay, so we'll prove this, but let's think about what it means. So what this says is that if you've got a set that's equinumerous with the naturals, two sets that are equinumerous with the naturals, you throw them together, still equinumerous with the naturals. Okay, what if you had, say, like 3 sets that were equinumerous with the naturals, and you took the union of all 3? Still equinumerous. Yeah? That is, if you have like A1 union A2 union AN, and all of the ANs are equinumerous with the naturals, well then, this chunk, equinumerous with the naturals. Okay, so take it with the next one, equinumerous with the naturals, and the next one, and the next one, and the next one. The whole thing is equinumerous with the naturals. Any finite union of denumerable sets is equinumerous with the naturals. Oh man, that's kind of wild. So in some sense, what this is basically telling you is that uncountable sets are like limits. Yeah? So the gist of it is that, like, with unions alone, you can't reach them directly. You have to look at like some kind of like a limit of unions, like an infinite union. Yeah? Oh, whoa, that's kind of wild. But if you think about, and I think I'm not spoiling anything here when I say this, since everyone has probably heard it before. We've all perhaps heard that the real numbers are uncountable. Has everyone heard that? I've at least alluded to it before. This is maybe not surprising if you think about the real numbers. After all, what is a real number? Well, you're used to seeing them probably written as like decimals, right? Or something like that, yeah? Like what is pi? 3.1415, right? Just keep going forever, yeah? Okay, well, each one of these digits is a natural number, yeah? Each chunk of digits is a natural number, right? So you could, in some sense, view a real number as like an infinitely long sequence of natural numbers, yeah? Some amount of it is to the right of the decimal place, but that can go on forever. You agree with this? Yeah? Okay, so in that sense, it does kind of feel like it's an infinite union of natural numbers. Now they are only digits like 1 through 9 or something like that, but you can imagine working in like a different base, right? Maybe you have like 90 digits instead of 9, right? You could have more digits and it would still all work out the same. You're just writing the same numbers in different ways. And so on some level, it really does kind of capture what's going on. That is, the the real numbers, this like kind of archetypal uncountable set, is something like a limit of unions of countable sets, of denumerable sets, of copies of the naturals. So let's build to that. Let's prove this. The union of two denumerable sets is denumerable. And it turns out, by the way, that we actually have a really nice construction that lets us build uncountable sets from denumerable sets that basically works like this union here. So, or like a limit of unions in a certain sense. So let's prove this. The union of two denumerable sets is denumerable. How would you start? What would you do?
Are denumerable sets. Therefore, there's a bijection between them. So between A and B.
Okay, I like this. Let's let A and B be denumerable sets. Then there exists bijections f from A to the naturals and g from B to the naturals. Let's construct a bijection. Let's call it H from A union B to the naturals. Yeah? Okay. So what should we do? Let's draw a picture and kind of think about what's happening. So in some sense, what's going on is you've got A here. This is like A1 all the way down through AN and so on forever, yeah? Okay, I'm writing them like with ones and so on, just because what I'm going to do here is I'm going to write the naturals here like 1, 2, 3, N, and so on forever. And what's really going on is that we're like, by indexing them, what I'm explicitly doing is I'm saying, hey, look, you can put them into a nice correspondence, right? In this blob-shaped diagram, I can make it so that the arrows all go straight across. Yeah? Same business with B. B is B1 down through Bn, and so on forever. If I take a copy of the naturals, 1, 2, 3, da da da, and da da da, forever, I can make it so the arrows go all across, yeah? The bijection. Okay, cool. If the arrows were twisted, I could reorder the things in A and B in my drawing of them. All right, so what could I do? How could I arrange these things? Think about the easiest case where A and B are totally disjoint, like where they have no elements in common. If they have elements in common, then the union's like a little bit messier, right? But if they have no elements in common whatsoever, what could you do? Just put them together. Yeah, you could kind of like alternate, right? Maybe our example with like the evens and the odds was actually a pretty good one, right? You could split the naturals into 2 chunks. You could send one of them to one of the chunks and the other to the other chunk, yeah? Okay. Really easy way to chunk the naturals up is to just turn them into evens and odds, yeah? That is, I can certainly take the naturals to the evens. This would be 1 times 2, 2 times 2, 3 times 2, and so on, n times 2, and so on and so on. And then I could take this chunk here to the odds, and this would have 1, which, by the way, is 0 times 2 plus 1, and then 1 times 2 plus 1, that's 3, and 2 times 2 plus 1, that's 5, right? And so on and so all the way down to 2n plus 1, and so on and so on. And I could just go straight across right there. Yeah? You agree with this? Okay. These 2 chunks right here, together, this whole thing, it's just the naturals, right? Okay. So in the case for like the you know, the most spread out A and B can be, where they're totally disjoint, this is not so bad. what if there's some overlap? What could you do? Oh, I guess you could take care of the overlap by itself. That's totally reasonable. Yeah.
You define their intersection, overlap,
Yeah.
and take it by like set point.
I see what you're saying. You're saying to do something like going like, hey, look, A union B is equal to A without B union B without A union A intersect B, right? Yeah, and then try to do it for each of these sets. Okay, totally reasonable. Now we enter some potentially slightly more difficulty in the sense that you could be like, well, what if some of these sets are finite, right? Now we have to kind of worry about like little chunks of the naturals or something like that. But we can totally do it. That's a very reasonable way to go about it and very kind of like procedural. I like that. Yeah. So you could take like the finite chunks. If any of these chunks are finite, you could map them onto some like initial segment of the naturals and then take the remaining stuff and you could do this like splitting argument. Yeah, totally reasonable. Perhaps even easier is that you could just take one of the sets and cut out the stuff that's in the other one, yeah? And you could send that stuff over. Or better yet, if you just look at what's going on here, it's like this here is F. That's what's taking us across. This here is G. That's what's taking us across there. And so all we have to do is we have to pick elements in A union B and send them across either to an even or an odd thing, yeah? So if something is in both A and B, you could just pick one of them to use. Maybe A, since it comes first in the alphabet. We could just do that. How about that? So if we do something like this, let's do this, okay? We can take H of X to be, say, O2F of X, if X is in A, and we could have it be 2G of X plus 1 if X is not in A. So we'll just use G if it happens to be in A. It could also be in B, but basically we'll just effectively only use one of the sets, yeah? Okay, cool. So if we do something like this, we say, all right, now do we hit everything? You may want to be careful there. We certainly at least have an injection, right? Do you agree with this? Okay. Then, since F and G are injections, so, oh, it's not two O's, so too is H. Maybe that's a little bit of hand waving for that piece, but I think everyone can kind of construct at this point the proof of the injectivity there in your head a little bit. The idea being that this one will never equal that one, right? One's even, one's odd. So the only things you have to worry about is if 2f of x equals 2f of y, but this just boils down to f of x equals f of y. And since f is a bijection, it's injective, that means x is equal to y, yeah? Same exact argument with g. Okay, cool. So if you buy that this is an injection, then let's look back at what we had just a moment ago when we said, hey, a set A is countable if and only if A weird less than or equal to the naturals. That is, if there's an injection from A into the naturals. Have we just constructed an injection from this union to the naturals? Okay, so it's countable. Yes.
Well, like this one now. Like, so for the odds, to get 1, you have to like multiply by 0. There's no 0.
Totally a reasonable thing to ask, yes. So what you've just picked up on is that this may not be a surjection. And in fact, probably isn't, yeah? Totally reasonable. Okay, and if we wanted to, do something that would potentially give us the possibility of getting a surjection, then we could shift g over a little bit, like 2 times g of x minus 1 plus 1 or something like that, right? And maybe that would help us. Okay, fine, cool. You could do like 2g of x minus 1, and that would also give you an odd number. Totally reasonable. But yeah, ultimately, though, it doesn't end up mattering. Why? Because we only need an injection. Yeah? Here's what we're going to do with that. Here's what happens. So since we have an injection, we can use that result that I just underlined on the other board there to say so by the second to last corollary, well, it's countable. Okay, so since the set is countable, if it's finite or denumerable, there's only 2 possibilities. Is the set finite, or is the set denumerable? Is the set finite? No, because A and B aren't finite. So it's either finite or denumerable. Since A is contained in A union B, and A is denumerable, it must not be the case that A union B is finite. So it must be denumerable. But that's what we wanted to show, is that the union of denumerable sets is denumerable. Does this feel reasonable to you? Perhaps you actually are feeling a little bit weirded out by part of it, namely the part where I claim that that having a denumerable subset implies that your set is also denumerable. Do you believe this? So I believe that we've perhaps, let me try to get back to, well, maybe actually this is not as immediately obvious. So I guess maybe this is like the little catch, like the tiny, like little extra piece. Catch, how do we know that how do we know that a finite set cannot have a denumerable subset? Maybe this seems kind of obvious, right? I think that if you just wrote this like this, people would go, okay, sure, if you've got something that is equinumerous with all of the counting numbers inside your set, then your set is certainly not finite, right? But we should at least, I guess, maybe perhaps make sure of this. So what would, instead of just writing it, what do you guys think? What would you say? This is actually a great kind of brain teaser one here. A piece that I should not just hand wave away nor give you the answer to right away, since it does feel reasonable.
Says it's going to equal the union itself, so union would be.
It might be equal to the union itself. That is, B might be equal to A, or B might be like a subset of A or something like that. Perhaps the empty set, which is also a subset, I guess. But yeah.
It's strictly subset, then there exist more elements in the union, so we can keep assigning more non-trolls.
So yeah, exactly. So okay, here's basically the gist of it. So suppose that A union B, or basically here's the catch. What we want to show is that A union B having a denumerable subset implies that A union B is not finite. This basically can be boiled down to like the following little like lemma. That is how do we show that a finite set S has only finite subsets, i.e. S prime contained in S implies S prime finite? How would you go about doing this? The answer is actually something that we've essentially already shown. So this goes back to when we were talking about finite sets, and we spent kind of a long time on this one. Basically, the idea is that if S is finite, then there is some initial segment of the naturals such that S can be put in a bijection with it. And here I'm going to do the same trick where I say, like, look, you can just write it, with the arrows directly across by putting the elements of S in a nice order like this, yeah? Okay, totally reasonable. Now, if you have a subset of S, then this bijection from S to some initial segment of the naturals, you could restrict F to that subset. Now, this may not be a bijection to that initial segment, but it is an injection. And we showed that if there is an injection F, or maybe call it G, how about? If there's an injection from S prime to an N, and G is not a surjection, then you get a new one, let's call it like G prime, from S prime to N minus 1. And you can keep going until you eventually get a bijection. Yeah? Do you remember this? Okay. So if you believe that, then effectively what that shows is that taking a subset of a finite set yields that that subset is itself finite. Yeah? What this says is that if S prime is not finite, then S is not finite. That's the contrapositive of this statement, right? Which is exactly what we're using right here. Feeling okay about that?
I have a question.
Yes.
Since we said like we restrict like the domain of F to be like S prime, and this is definitely an injection. Is that like a fact we can just take it as it is, or we have to prove it?
Oh, that a restriction of an injection is itself an injection? This is a good question. It by itself is perhaps not immediately obvious. You should always prove things. Yeah, good idea. It is fortunately relatively easy to prove. That is, F restricted to S prime is a function from from S prime to that initial segment, and it's defined by F of S prime x is in fact equal to F of x for all x. Yeah. So it inherits the injectivity automatically, yeah? If that makes sense? Cool. Okay, so the answer is that we did this already in the last section, if that makes it any clearer. Okay, cool. So it works, good. Union of denumerable sets is denumerable. Hence, any finite number of unions of denumerable sets is denumerable. So this gives us quite a lot of nice consequences. The first of which is the fact that we have said out loud that I will now formally write down, I guess, as a theorem. That is, any finite union of denumerable sets is denumerable. And what I'll show you with this is that something even crazier is true. Okay, I have a long-running idea for an invention, which is I think would be really good. I think it would be really cool if there was like a giant eraser that went all the way across the whiteboard on like a motor, and I could just press a button and it would go zoop, zoop, like a big squeegee. Wouldn't that be great? It'd be really expensive, and I'm sure no one would buy it, but I would make it. It would be cool. It would probably like end up ripping off some professor's fingers, so that's why we don't have that. But all right, corollary. Any finite union of denumerable sets is denumerable. And since we're almost at the end, we'll just use this entire board all at once, a very long line here, to get to the last theorem of this section, which is crazy. Let me write it. Okay. The set of the naturals cross the naturals, the Cartesian product of the naturals with itself. One copy of the naturals for each natural number. That's denumerable even. What? Oh my gosh. That's crazy. That's not even a finite union, right? Think about what this is. This has 1, 1, 1, 2, 1, 3, so on and so on. It's got 2, 1, 2, 3, or 2, 2, 2, 3, and so on forever. And this goes all the way down. Each one of these rows is basically just the naturals, right? Look at like the second coordinate. Yeah? It is a countable number of copies of the naturals, and it is still itself countable, right? Whoa, whoa, that's nuts. Okay. This is nuts. How do we prove it? What would you do? How would you go about proving it? Can you think of a clever trick? Let's show that it's countable. Since countable implies either finite or denumerable, and this is certainly not finite, we get denumerability just from countability automatically. All right, so what would you do? Well, the construction is pretty nice. So, set f to be the function from the Cartesian product of the naturals with itself to the naturals by f of ab equals 2 to the a minus 1 times 2b minus 1. We show f is injective, which yields that n cross n, weird less than or equal to sign, the naturals, and thus that it is countable. Yeah? That was one of our first theorems today. Okay, cool. So, how do we show injectivity? To wit, let's suppose that 2 to the a minus 1 times 2b minus 1 equals 2 to the c minus 1 times 2d minus 1. Okay, so we show that a equals c first. How? Well, suppose not. Then, without loss of generality, we'll suppose that, say, A is, I don't know, greater than C. Yeah? Be a trichotomy, one's got to be bigger than the other. So, if A is bigger than C, let's basically just divide over by 2 to the C minus 1. Yeah? Okay. Then I get 2 to the A minus 1 minus C minus 1 times 2B minus 1 equals 2D minus 1, i.e. 2 to the A minus C times 2B minus 1 equals 2D minus 1. And A minus C is greater than 0. Yeah? But that means that this side is divisible by 2, and this side's odd. That can't happen, right? But this is a contradiction since the left-hand side is even and the right is odd. Okay, so A is equal to C. Now, divide those two off and you get 2b minus 1 equals 2d minus 1. That's just algebra, right? Add 1 to both sides, multiply by 1/2 on both sides, you get b is equal to d. So A is equal to C. That b is equal to d is just algebra after this. So that is my very quick and abbreviated proof of that. That takes us like 2 minutes over the end of class. Sorry. Weird, crazy, right? A denumerable union of the naturals is itself denumerable. Oh, whoa. How on earth are we going to get to these countable sets? Or these uncountable sets? It feels crazy. We'll see it next time, and it's something familiar that you've seen before. So I'll see you then. Have a great day.